Hello and welcome once again to the Aakash Byju's JEE channel. My name is Attiullah and we are back with another live session of JEE Mission 2022. As always, before we start, just let me know if you can see me properly and you can hear me clearly. Give me a thumbs up, give me a yes, and then we are good to go. Good evening, Captain Jack Sparrow. Good evening, Swastika. How are you guys? One of the most regular people on this channel. Alright, so I see thumbs ups. Alright, so we are good to go. So on agenda today is current electricity again. In the previous session yesterday, we discussed some concepts. Now we are going to continue our discussion, and in this session, we're going to talk about some conceptual questions and previous year questions. Okay, so the format remains the same. I'm going to throw questions at you and you need to take out your pen, your notebook, be ready with that, and we are going to solve the questions again. The first thing you are going to tell me is how do we go about approaching a particular problem. Okay, once the concept is clear, then we'll go ahead and solve the question. Alright, so are you guys ready? Utsav, good evening. Saudagar, good evening. Hi. Alright, so are you guys ready with your notebook and pen? So if you're ready, let's get started with this session. Alright, let's get started with the first question. Okay, what does the question say? We have a DC main supply. Okay, what do we have? A DC main supply of EMF 220 volt. So what is it? It is over here. And it is connected across a storage battery. You can just think of it as a battery of EMF 200 volt through a resistor 1 ohm. So here is the battery of 200 volt we are talking about, and here is the resistor 1 ohm. Now the terminals of the battery are connected to an external resistance R. So this is our resistance R, which is connected to this battery. Now we need to find out the minimum value of R so that the current passes through the battery to charge it. Okay, so the current should pass through this battery in a manner so that it is charging the battery. Okay, now is the question clear? Are you comfortable with the question? If you are, then the first thing you need to tell me that what does it mean to charge a battery. Okay, the main concept involved here is how do we charge a battery. Okay, do you have any ideas? So let me know. Okay, so we are talking about charging a battery. How do we charge a battery? What is so special about charging a battery? And hence, what is discharging of a battery? Charging a capacitor. So Swastika, not really. We don't have a capacitor in the circuit. We are talking about charging a battery. How do we charge a battery? Okay, so you know there are rechargeable batteries. Yeah, there are rechargeable batteries. You plug them in a socket, and then what happens? They get charged. But how do they get charged? What is special in the circuit? And if I have to give you a hint, there is something special about the direction in which the current is flowing through the battery. Are you guys aware of that? If yes, please let me know. That is the main concept in this question. Reverse the chemical reaction. Awesome answer, Tanmay. We need to reverse the chemical reaction. Absolutely. And how do we do that? No current used from the battery, Arnav, that is right, but there is something more to it. So Tanmay, I think here is correct, reverse the chemical reaction. But how do we reverse the chemical reaction? What do we do to reverse the chemical reaction inside the battery? So Somnath is saying supply EMF. Yes, that's more or less right. So this is how we charge a battery. Now in a battery, so let's say we connect a battery to an external resistor. In this case, what is going to be the direction of flow of current? The direction of flow of current is going to be like this. It is going to go out of the positive terminal of the battery in the external circuit. So what we are talking about is the external circuit, not the direction of current inside the battery. So in the external circuit of the battery, the current is going to flow out of the positive terminal. Correct? Okay, that's the usual way a battery works. Now when battery is working in this way, it is supplying the current. Okay, so this is the usual way in which a battery works. But if we have to charge a battery, then what do we need to do? We need to take this battery and we need to apply a higher EMF source. Okay, so if this has an EMF of V1 and this has an EMF of V2, then we have to supply it or connect it with an EMF source which is greater than that of the battery. And in that case, this EMF is going to force a current through the battery. Okay, now notice what is the direction of current. The direction of the current is opposite. In the external circuit, now the current is going into the positive terminal. Is that right? This is how we charge a battery. So the question here is, what should be the minimum resistance R so that we are charging a battery? Is that right? Okay, so how do we go about solving this question? Okay, let's say there is a current I coming over here. In the circuit, let's say there is a current I coming over here. Okay, now we see that this current is going to get divided. Okay, this current is going to get divided. So let's say this is I1 and let's say this is I2. Is that correct? Okay, so the current is going to get divided into I1 and I2. Now the key here is that this I1 should be positive. Okay, what does it mean? Suppose I have assumed the direction of I1, and if it comes out to be positive, it means that the direction for current we have chosen is correct. Now if the current is in this direction, then we see that this is going into the positive terminal of the battery, and hence this battery is going to get charged. Is that correct? That is the key concept of this question. So all we have to do is, we have to find this I1 and we have to see what is the condition so that this I1 is positive. Is that right? So let's go ahead and solve this question. Okay, so I'm assuming a current I over here, I'm assuming a current I1 over here, and I'm assuming a current I2 over here. Now this becomes very clear from the junction law. If we apply the junction law over here, then we can say very confidently that I is going to be equal to I1 plus I2. Is that right? No problems over there. Okay. Now what is I2? Now let's think about what is I2. So this resistance is connected between these 2 points, and those 2 points are basically the terminals of the battery. Okay. So what is the potential difference across this resistance R? The potential difference is going to be 200 volt, which means we can say that I2 is going to be 200 divided by R. Is that correct? Okay. So we have taken this resistor R and we see that it is connected to the terminals of this battery. Can we see that? So what is the potential difference across this resistor? It is 200 volt. So what will be the current through it? It is going to be 200 divided by R. Plain and simple. Okay. Now in our equation, I is equal to I1 plus I2, we have I as well. Is there a way we can find out what is I? Okay, can you tell me a way in which we can find this current I? Can you tell me? Any guesses? How do we proceed to find out what is going to be the value of I? I need to find out what is the current I. Any guesses? The objective is to find I1. So we have found out what is I2. The only thing remaining is we need to apply a method to find out I. And Tanmay is absolutely right. We can apply loop law. We can use KVL. In which circuit? Let me name that loop so that you are comfortable with it. I'm talking about going from A to B to C and then back to D and A. Okay, I'm going to go clockwise in this circuit. Okay, I can do that and then I can find what is the value of the current. Okay, so let's do that. Okay, so we are here, we are starting from A. Okay, when we are starting from A, then we are going across this battery and we are going from the positive terminal to the negative terminal, which means the change in potential is going to be negative. So we will have to write minus 200 volt over here. Correct? Okay. Now what you notice here is that whatever is the current I over here will be the same current I over here. Okay, it's the same branch. Okay, it's the same branch throughout. So this current is also going to be I. So now we are going to go across this resistor. And what is the direction in which we are going? We are going in the direction of the current, which means that the potential change is going to be negative. Okay, that is going to be minus I into 1. Simply IR, but negative. Correct? Now where are we? We are over here. We are going to go across this EMF source and we are going from the negative terminal to the positive terminal. So then we have to write plus 220 volt. Okay. Now we are at D and we are back at A. The loop has been completed, so this should be equal to 0. Is that right? So from here, what do I get? I get I is equal to how much? We get I is equal to 20 ampere. Is that right? So we get the value of I. Now all we have to do is substitute it over here. Okay, so let's do the substitution. Let me make some space for that and let's do the substitution. So I has a value of 20. This should be equal to I1 plus I2. What is I2? I2 is 200 divided by R. So from here, what do we get? We get the value of I1 as 20 minus 200 divided by R. And what did we decide? That if this current is charging the battery, then the current has to be in this direction. That is, this is the assumed direction, and if direction has to be correct, then I1 has to come out positive. Is that correct? So we can say that this I1 should come out to be positive. And when we do that, when we solve this inequality, we are going to get R greater than 10 ohm. Can you see that? It's a simple inequality we can solve, and we can say that R should be greater than 10 ohm. Okay, so what is the condition for the resistance? The condition is that R should be greater than 20 ohm. Now we can go ahead and look at the options. What are the options? We have 7 ohm. Is that the right answer? Of course not. 9 ohm, certainly not. It has to be greater than 10 ohm. So what will be the correct option? The correct option is going to be option C, 11 ohm. Is that correct? Are we clear with this question? There was the most important concept in this question was that how do we charge a battery? What does it mean to charge a battery? And what does it mean? It means that in the external circuit, the current has to flow into the positive terminal of the battery, and then we're going to charge the battery. Is that right? Perfect. Any confusion, any problem, ask away, don't hesitate. If there's even a slight doubt, do let me know. Okay? Now, as always, the objective is to take away fear of JEE from you. So give me a difficulty level, rate the difficulty level for this question. I won't say it was a very straightforward question. It was very conceptual, but what do you think is the difficulty level for this question? Where does it fall on the difficulty spectrum? Okay, Captain Jack Sparrow, very interesting answer. 3.14 out of 5. Awesome. Good use of pi. Arnav also says 3, Tanmay says 3, 2 out of 5. Alright, so this falls somewhere between easy to moderate category. Okay, so this was a question asked in previous year JEE papers. So not that difficult to solve if we are clear with the concept. Right, ready for the next question? Here we go. Alright, let's look at this question. So we have a 9-volt battery with internal resistance of 0.5 ampere. 0.5 ohm. So here is our battery. Now see that this battery is containing the internal resistance as well. Okay, so here is our battery and it is connected across an infinite network. Okay, do you see this infinite network? 1 4 1 1 4 1 1 4 1, and this pattern is going to repeat itself infinitely. Okay, now all ammeters A1, A2 and A3 and the voltmeter is ideal. Okay, so what is A1? A1 is going to measure the current over here, A2 is going to measure the current over here, A3 is going to measure the current over here. The important thing is, what is this V measuring? Is V measuring the potential difference across the battery only? Okay, remember that this battery has internal resistance. So this potential difference that we are talking about is for the entire battery, which includes the internal resistance. Okay, so we have to basically find out what is the terminal potential. Is that correct? Alright, so what do we need to find out? We need to find out what is the value of A1 and we need to find out what is the value of V. Okay, is the question absolutely clear? And if the question is clear, I'm going to ask you first, how do we approach this problem? It's a very typical kind of problem, okay? Infinite ladders, infinite circuits. It's a very typical kind of problem. Can you throw some light on how do we go about solving this question? First, I want to know from you. How do we approach a circuit where we have infinite network? Now, these questions appear difficult, but if you're able to visualize them properly, then it's not that difficult at all. Alright, so Captain Jack Sparrow says, take out one pattern and add it with the infinite pattern. You are absolutely right. Okay, so we are going to go ahead and use that method. Alright, so now what I'm doing is, let me rub this off. Now what I'm concerned is, I'm concerned what is the resistance across these 2 points. So I'm calling them points A and B. And I'm also concerned with what is the resistance between these 2 points, and I'm calling them points C and D. Alright? Okay. Now for some time, I'm going to remove this battery. For simplicity, for visualization, so basically the battery is over here. This is point A, this is point B, this is point C, this is point D. Okay, but for simplicity, I'm for the time being removing this battery. I'm going to put that back in. Don't worry. Okay, now this is the situation. Alright. Now what I want you to focus is, I want you to focus on this part of the resistor. I want you to focus on this. Okay, so the part which is out of this loop that I have drawn, just forget about that. Okay, just forget about that for a second. Okay, keep that out of the circuit. And then if I redraw that circuit, so what is this? This is my point C and this is my point D. Okay, that's what I have done. So just forget about the circuit to the left of the loop. Just forget about that. And I've redrawn that circuit here. This is point C and this is point D. Is that right? Okay, now what is it that we observe? Okay, now let me erase this off. Now tell me, what is it that we observe over here? What pattern is repeating itself? So if we talk about the effective resistance or the net resistance between points A and B, okay, just think about the net resistance, how the loop is structured, how the network is structured about point A and B. And just think about the structure about point C and D. Okay, do you find something very similar? Okay, and Tanmay is absolutely right, the circuit remains the same. Okay, so you look at this pattern AB. What do you see? 1 4 1, then 1 4 1, and then 1 4 1, and this continues. Now you look at C and D, you look at the point C and D, and then see what is happening. 1 4 1, 1 4 1, and this pattern is continuing. Okay, now what does it mean? It means that since the circuits are absolutely the same, then the resistance between points A and B will be the same as the resistance between points C and D. Are you convinced with this point? Let me know. So my argument over here is, since the pattern between A and B looks exactly the same as the pattern between C and D, then the resistance between A and B is going to be absolutely same as the resistance between points C and D. Are you able to visualize that? Okay, this has to be absolutely clear. If you're not clear with this, let me know. I'm going to explain again. Don't worry about that. But this point, this is the key element in this question. Okay, is that clear? Let me know. Awesome. So this is absolutely clear. So what I'm going to do is I'm going to simply redraw this circuit. So I'm going to redraw this circuit, and what I have done is, this is point A and B. So whatever is the resistance between points A and B, I'm calling that resistance as R. The resistance between points A and B, I'm calling that R. And this is point C and D, is the same as the resistance between point C and D. Is that correct? So I'm going to call that R as well. Alright. Can we use Wheatstone bridge over here? It's not really a Wheatstone bridge, Tanmay. It's not even an extended Wheatstone bridge. Okay, in extended Wheatstone bridge, what we have is we have identical paths. So from going from A to B, we should have identical paths. Okay, that is not the case over here. We don't have identical paths. Only when we have identical paths, then the corresponding points become equipotential, and then we can throw away the resistor between them. That is what happens in Wheatstone bridge or extended Wheatstone bridge. But if you look at the path from going from A to B, we don't have equivalent paths. So this is not a Wheatstone bridge or an extended Wheatstone bridge. Okay, so we are going to reduce the circuit in this manner. So finally, what is the conclusion? That the resistance between C and D is R. So the resistance between A and B is also going to be R. So from this circuit, if we find the resistance between A and B, that should be equal to R. That is our approach. So let's go ahead and do that. Okay, so here is the resistance R. So how do we find out the equivalent resistance? Okay, so what we see here is that this 4 and this 3 is in parallel, and that is going to be in series with this 1 and 1. Okay, so I'm sure that you guys are well versed with series and parallel combination, so I'm going to directly write what is the equivalent resistance. Okay, so the parallel combination of 4 and R is going to give me 4R divided by 4 plus R, R1 R2 upon R1 plus R2, correct? And that equivalent combination is in series with 1 ohm and 1 ohm. So this should be plus 2, and that is the equivalent resistance between A and B. And what is that? That equivalent resistance between A and B is also R. So here we have this equation. So let's quickly solve this equation. So this is going to become 4R, and this will become 8 plus 2R, and this 4 plus R is going to go that side and become 4R plus R square. So this 4R and this 4R gets cancelled. We have R square minus 2R minus 8 is equal to 0. And we can factorize that in a very simple manner. So this is going to be minus 4R plus 2R minus 8 is equal to 0. Simple quadratic equation. So this is going to give me R minus 4 into R plus 2 is equal to 0. So the answer here, or not the answer, but the equivalent resistance in this case is going to be 4 ohm. Okay, obviously we are going to neglect minus 2. Negative resistance doesn't mean anything over here. Alright, so what is the resistance across, the equivalent resistance across AB? It is 4 ohm. And once we have figured that out, we are going to go back into our circuit. And then between these 2 points A and B, this entire circuit, what is the equivalent resistance? The equivalent resistance is 4 ohm. So I have redrawn it in this circuit like this. Is that correct? So the circuit has reduced to this simple circuit. Okay. Now what is the current going over here? Can we find out what is the current? Very simple. Now this 4 ohm and this 0.5 ohm is going to be in series. So the current which is going to go through ammeter A1 is going to be 9 divided by 4.5. That is 2 ampere. Is that correct? Okay, so we have found out what is the current. Now we also need to find out what is the potential difference. Okay, what is the potential difference? And we know that if the current is flowing in the usual direction, by usual what I mean, that in the external circuit the current is coming out of the positive terminal. So the current is flowing in the usual direction, and if that is the case, then the terminal potential is given by E minus IR. Is that correct? So this is equal to, what is EMF? EMF is 9 volt minus I. What is I? I is 2 ampere. We have found that, and R is 0.5 ohm. So this is going to give me 8 volt. Okay. Captain Jack Sparrow is asking 4.5 kaise? See, this is 4 ohm. The internal resistance is 0.5 ohm. Okay. So in this circuit, the internal resistance 0.5 ohm and 4 ohm are going to be in series. That's it. That's how we got 4 plus 0.5 is equal to 4.5. Okay. So here we have V is equal to 9 minus 2. So basically we have calculated what is V. So that is 8 volt. The current is 2 ampere. So what is our answer? That the reading of ammeter A1 is going to be 2 ampere. The voltage, the potential difference, or the reading of the voltmeter is going to be 8 volt. So let's look at the options. So reading is A1 is 2 ampere, that is absolutely right, but we don't have any option for V is equal to 8 volt, so none of those options are going to be correct. So option A is going to be the right option. Is that right? Okay, so are we clear with the question? Are we clear with the solution? Are we clear with the concept how to deal with circuits which have infinite ladders? Okay, so Astika is asking, is there any physical meaning of negative resistance? Can negative resistance mean conductance? So in the circuits that we are using, in electrical circuits we are using, I don't think negative resistance would have any physical significance. Negative resistance does not mean conductance. Okay. the reciprocal of resistance is conductance. Okay, so if a resistance has a high value of resistance, then it is not a good conductor, which means it has poor conductance. So conductance is the reciprocal of resistance. All right, but the circuits that we are using, then in those circuits, at least to the syllabus that we are talking about, then the negative resistance does not mean anything. But if at all it means anything in any other kind of circuit, honestly, I'm not really sure about that. Okay, but for us, we are always going to take the resistance as positive. All right, now give me the difficulty level for this problem. Quickly let me know what do you think of the difficulty level over here. Three out of 5, 2 out of 5, 4 out of 5. All right, I'll give it somewhere between, somewhere at 3 out of 5. I think that's fair. Okay, if only you know how to deal with infinite networks, then it should not be a problem at all. It's all about visualizing and seeing what pattern is repeating. If you're able to identify what pattern is repeating, it's not difficult at all. Okay, perfect. Mathematics classes is asking, is type की ही questions, can you highlight that? जेई में आते हैं, बिल्कुल इस तरह के क्वेश्चन ही जेई में आते हैं, क्योंकि ये सारे क्वेश्चंस जेई में आए हुए हैं, राइट? तो ऐसे क्वेश्चंस जेई में हम बिल्कुल एक्सपेक्ट कर सकते हैं. ओके, परफेक्ट. नाउ वी गो टू द नेक्स्ट प्रॉब्लम. व्हाट डू वी हैव हियर? ओके, सो फॉर द सर्किट शोन वी हैव R1 is equal to 1 ohm, we have R2 is equal to 2 ohm, E1 is equal to 2 volt, and E2 is equal to E3 is equal to 4 volt. Okay, just look at the circuit. Then we have to find out what is the potential difference between points A and B. Okay, so these 2 points are A and B. We have to find out what is the potential difference between points A and B. Okay, is the question clear? Now, if the question is clear, then I'm going to ask you first, how do we approach this problem? Okay, it's circuit. Remember, we have to look at different things. When you are talking about circuit, we have to see if there's series parallel combination, if there is symmetry in the circuit, okay, is there a Wheatstone bridge, and we know there are a series of steps that we need to follow and identify what is the method that we should use to solve this question in the most effective manner. Okay, any hints, any ideas, how do we go about approaching this question? Any guesses? KVL. Okay, Tanmay is saying something. Can you highlight that, please? Taking two different loops and applying loop law. So basically we are saying KVL. A lot of answers, KVL. Alright, see. We can solve any circuit question using KVL. There's no doubt about it. Okay, we can solve any circuit question using KVL. But the question is, should we use KVL? Is that the most effective method? Okay. So of course you can solve it by KVL. You can use loop law and solve this question. But we need to get a little smarter than that. Okay. So can you attempt, or can you think of any other method that we can employ over here? For sure, any circuit question, be it how tedious it is, it may happen that in a circuit there are 10 variables and 10 equations, then also you can solve by KVL. But that's not the most optimum way of solving this question, okay, or any question. We have to see if there's series parallel combination, okay, then we have to see if there's a Wheatstone bridge, then we have to see if there's symmetry, and if there's no symmetry, then we look at combination of batteries, okay, combination of cells. We look at combination of cells. If we don't find combination of cells, then probably we can use superposition. When we have exhausted all of these methods, then finally when we have no resort, then we go for KCL, KVL. Okay, so I'm going to give you a hint. Okay, I'm going to give you a hint. So what we can do here is, first of all, it's very straightforward to see that this is R1 and this is R1, and they are going to be in series. Do you agree? Okay, do you agree? This is R1, this is R1, they're going to be in series because the current through both of them are going to be the same. There is no branching when we go from one resistor to the other. So they are in series. So we can club them. Okay, now this R1 over here and this R1 over here is also in series, so we can club them together. So what I'm going to do is I'm going to club them together and I'm going to redraw this circuit. Okay, so this is how much? This is 2 volt, this is 4 volt, this is 4 volt, and this 1 and 1, when we club it together, we are going to get 2 ohm. This 1 and 1, when we club it together, we are going to get 2 ohm. And then this R2 is how much? This R2 is 2 ohm as well. Okay, so the circuit is like this. This is point A, this is point B. Is that right? Okay. Now, can you think that this 2 volt battery has a 2 ohm resistor in series? Okay, so can we think, okay, it's not necessary, but can we think that we think of this as one battery which has internal resistance? Okay, a lot of you are saying that symmetry, but unfortunately I don't see any symmetry in this question. Okay, unfortunately I don't see symmetry. So a better approach, in my opinion, would be treating this battery and this resistance as a part of a battery which has internal resistance. Can we do that? Okay, in a battery with internal resistance, what happens? The resistance is simply in series. Is that right? Okay, so I can think of this as a battery, I can think of this as a battery, and I can think of this as a battery as well. All of them have internal resistance. Can I do that or not? First, I want to be clear over here. So let me know if you have any problem if I'm taking this approach. Can I do that or not? All right. So what I'm going to do is I'm going to take them, I'm going to approach them as batteries with internal resistance. Okay, now if we do that, the circuit is going to be simplified like this. Okay, so this is a battery, this is the positive terminal, this is the negative terminal, this is the battery, this is the positive terminal, this is the negative terminal, this is a battery, positive terminal, negative terminal. Okay, now are all these cells between points A and B? Can you check and tell me? Okay, all these points are between A and B, which means all these cells are in parallel combination, and we can use the result for combination of cells when they are in parallel combination. Can we do that? Of course we can do that. So basically what are we going to do? We are going to find the equivalent EMF and equivalent internal resistance between the points A and B. Do you agree? Captain Jack Sparrow is asking, can we apply series combination even if there is a cell between resistors? Absolutely, Captain, you can absolutely do that. So how do we check for series combination? When we are going from one resistor to the other, is there any branching? Okay, let me go back and clarify that for you. No worries. Okay, now if we are going from this resistor across the battery and through this resistor to this point, then is there any branching? No, there is no branching. Okay, and if the current is I over here, then the current is going to be I over here and the current is going to be I over here. So through both these resistors, the current is the same, and that is the definition of series combination. The current has to be same in both the resistors. Okay, so even if there is a battery in between, no worries, we can still take them in series combination. Okay, so I hope that is clear. Perfect. So how do we go about finding the equivalent EMF? So the equivalent EMF is given by, do you remember this? The summation of E by R divided by the summation of 1 by R. Okay, and what is 1 upon R equivalent? The equivalent internal resistance, it is going to be 1 summation of 1 upon R. Do you recall this? Okay, so that is what we are going to follow over here. Okay, so let's do the substitution and figure this out. So what do we have here? We have the EMF in this one, the first one. We have the EMF as 2, then divided by 2, plus what is the EMF here? The EMF is 4 and divided by 2, plus what is the EMF here? It is 4 and divided by its internal resistance 2. and this has to be divided by the summation of 1 by r. So we'll have 1 by 2 plus 1 by 2 plus 1 by 2. Okay, so in the denominator we are going to get 1 upon r equivalent. Remember that. In the denominator we are going to get 1 upon r equivalent. Okay, so if we add this up, what do we have? We have 5 in the numerator and we have 3 by 2 in the denominator. So what is r equivalent? R equivalent comes out to be, so 1 upon r equivalent is 3 by 2. So r equivalent is going to be how much? R equivalent is going to be 2 by 3. Okay, and what is the equivalent EMF? The equivalent EMF is going to be 10 upon 3 volt. Is that clear? So mathematics classes says, according to my solution, answer is 3.33. You are absolutely right. The answer is absolutely correct. So we are almost there to find the solution here as well. Okay. So what have we found out? We have found out that the equivalent EMF is 10 by 3 volt and the equivalent internal resistance is 2 by 3. So let me redraw this circuit. So I can draw the equivalent circuit like this. So between points A and B, what is the equivalent EMF? The equivalent EMF is 10 by 3 volt and the equivalent internal resistance is 2 by 3 ohm. That is the circuit now. The circuit has reduced to this. That's it. That's it in the circuit. Okay. Now we can see that these points A and B is part of an open circuit. Okay, there is no closed circuit over here. Okay, the circuit has disappeared. So internally in the branches, the current would be there. Okay, internally in this branch, in this branch, in this branch, the current would be there. But if we take them as a whole, then this is an open circuit. And if this is an open circuit, there's going to be no current through this branch. And if there's no current, then the potential difference is going to be equal to the EMF. Okay. So this is E minus IR, but I is 0, so the potential difference is going to be simply equal to EMF. So what is the potential difference between A and B? The potential difference is 10 by 3, or we can say 3.33 volt. And that is going to be my answer. Is that right? Is that clear? Any problem here? Okay. So instead of applying KVL blindly, we should exhaust all our options. Okay, so we saw that by using equivalent combination, this question is much easier to solve. Otherwise, you'll have to assume currents, you'll have to assume, you have to apply junction law, you have to apply KVL, all that stuff. KCL, KVL should only be your last resort. Is that correct? Okay, so using combination of cells, we have arrived at our answer. The potential difference between A and B is going to be 3.3 volt. Clear? Perfect. Now I'm going to give you another method. Okay, I'm going to give you another method which is still better than KCL, KVL. Okay, this method is called superposition. Okay, in this particular question, superposition is also going to help. It is going to be slightly more tedious than the previous method, but we can use superposition also, and I'm going to show you. Okay, I'm going to show you. So how superposition principle works is that we are going to short. So let's say we have 3 batteries. So we are going to short 2 batteries and find the current due to that one battery. And we are going to repeat this process 3 times. So shorting the other 2 batteries, we are going to find the current through one battery. And the principle of superposition says that the battery work in a manner such that the other batteries do not exist. So the net current in the branch will be the algebraic sum of all the 3 currents. Okay, so let's take that approach. But a little caveat here, okay, you should be comfortable with quickly applying series and parallel combination. Okay, quickly dividing voltage, quickly dividing current. Okay, you should be well versed with that. Otherwise, this is not going to be very easy for you. Alright, so let's go. So the first thing I'm going to do is I'm going to short these 2 batteries. Shorting these 2 batteries means that you are connecting both their terminals, so this battery becomes non-existent. Okay, we are simply shorted this battery means you can remove the battery and you can simply attach a wire over there. Okay, that is what shorting means. So how do we technically short? If we short it, we are connecting both the terminals. So the current is not going to, the current is going to get, if the current is coming from here, the current is going to get a resistance-less path. So all the current is going to go through this wire and no current is going to flow through this battery. So for all practical purposes, we can simply replace this by a wire. Okay, done. Now what is the battery which is remaining? The 2 volt battery is remaining over here. So this is 2 ohm and this is 2 ohm and they are in parallel combination. So 2 and 2 in parallel combination is going to add up to 1. And that 1 is going to be in series with 2 ohm. Do you agree? So 2 plus 1 is going to be 3 ohm. And that's what I said, you have to be very good with series and parallel combination, applying that quickly. I'm not going to redraw all the circuits, that is going to become very tedious. Okay, it's simple, very simple. This 2 and this 2, they are in parallel. So 2 and 2 is going to give me 1. Okay, and then this one with this 2 in series. Now this is going to be in series with this 2 ohm, is going to give me 3 ohm. So what is the current that is going to come out of it? The voltage is 2 divided by 3, which is the resistance. So the current supplied by this battery is going to be 2 by 3 ampere. But we want current over here. Okay, we want current over here, because I want to find what is the potential difference between A and B. So I want the current over here. So what is going to happen? So this 2 by 3 is going to come over here. At this junction, it is getting divided into a resistance 2 ohm and 2 ohm. These are equal resistances. So the current is going to be divided equally. Okay. So this is going to become 1 upon 3 ampere, and this is also going to become 1 upon 3 ampere. Is that correct? So what do we see here? The first case is that there is a current 1 upon 3 ampere going in the downward direction. It is going from A to B. The direction of current is important here as well. Okay, don't forget that. So because of the first battery, I have found that the current in this branch AB is 1 by 3 ampere. Is that correct? Are we comfortable with this? Any problem? Let me know. If you are comfortable with this, then I'm going to do this quickly for the next 2 batteries. So we have found the net current, and then we have divided it into the 2 branches. Both of them had equal resistance 2 ohm and 2 ohm. So the current is also going to get divided equally. Clear? Alright. So now let me rub this off. And then we are going to short the other 2 batteries. So I'm going to short this battery and I'm going to short this battery. Okay. In this case, what is going to happen? This 2 ohm and this 2 ohm are going to be in parallel. Can you see that? So 2 and 2 is going to give me 1, and that is going to come in series with this 2 ohm. Okay. So 2 and 2 gives me 1, 1 and 2 gives me 3. Are you comfortable with that? And the current I want is this current over here. I want this current over here. I want the current in branch AB. So what will be the current? So the equivalent resistance comes out to be 3. The potential difference or the voltage is 4. So this is going to be 4 by 3. Any problem here? So the current now in this branch due to this battery is going to be 4 by 3, and notice the direction. The direction is upwards. Okay? Is that clear? Any problem over here? So I have found out the current due to this middle battery. Now I'm going to repeat this process for the third battery. So I'm going to short these 2. I'm going to short these 2, and then what do I see? I see this 2 ohm and this 2 ohm is going to be in parallel combination. So 2 and 2 is going to give me 1, and that 1 ohm is going to be in series combination with this 2 ohm. So the equivalent resistance becomes 3 ohm. So the current over here, mind you, the current over here is going to be 4 by 3 ampere. Okay, but that is not the current we are looking for. We are looking for this current. Now when the current has reached over here, it is getting divided into 2 branches. Okay, so this has 2 ohm, this has 2 ohm. Both the resistances are equal, which means the current is going to get divided equally. So what will be the current in this branch? The current in this branch is going to be 2 by 3 ampere. And what is the direction? The direction is going to be downwards. Okay, so this is going to be 2 by 3 downwards. Now what do we need to do? We need to take the algebraic sum, which means we have to take care of the direction of current as well. So the net current due to all the 3 batteries is going to be 4 by 3. Upward current I am taking as positive. So 4 by 3, then minus 1 by 3 and minus 2 by 3. What is this going to give me? This is going to give me 1 by 3 ampere. Is that correct? Alright, so what is the net result? The net result is that the current over here is 1 by 3 ampere. Do you agree? And if you have found the current, then it is very easy to find the potential difference over here. Okay, all we have to do is we have to find the terminal potential difference. So what will be the terminal potential difference? The terminal potential difference is going to be E minus IR, because the direction of current is usual. Okay, so what is E? E is going to be 4 volt over here minus I, which is 1 by 3. And then what is R? R is 2. So this is going to give me 10 by 3 is equal to 3.33 volt. Yes, Tanmay, I'm using upward direction as positive. Okay, you can choose the other way also, but it is going to give you the same result. Alright, Captain Jack Sparrow is asking, sir, if current has direction, then why it is not a vector quantity? Captain Jack Sparrow, it is not a vector quantity because it does not follow the vector addition, the vector law of addition, the triangular law of addition or polygon law of addition. Okay, so there are some quantities which have directions, but they are added like a scalar. Okay, they don't obey that method. Okay, Arnav is saying, sir, confusing method. Arnav, this is a slightly complicated method, but that's what I said, that you have to be very good with series and parallel combination. Okay, so if you are good with series and parallel combination, if you can do that quickly, this is indeed a very good method. Okay, it is going to be very helpful to solve questions quickly, given that you are very comfortable with series and parallel combination. Okay, but it's not the only method. You can choose which method works for you, and that is completely fine. Is that correct? Alright, so we can solve this question in this manner also. In a question where we had only 2 batteries, this question would have been faster. Okay, we could have been able to solve this question much faster. In this case, we had 3 batteries, so we had 3 scenarios. Okay, but I just wanted to show you another method of solving questions. Okay, so you can have another question in which this method might be the easier method. Alright, so I hope that is clear. Now tell me, what do you think of the difficulty level of the problem, and then we can move to the next question. What do you think of the difficulty level of this problem? .5, 2 out of 5, 3.5. It's fair. It's fair. It wasn't very straightforward, and a lot of people would be tempted to use KCL, KVL directly. Okay, but I'm just showing you there are better methods. So until and unless we have exhausted the better methods, we should not jump to KCL and KVL. All right, perfect. So now let's go to the next question. All right, so we have now question on electrical instruments, which is also a very important part of this chapter. All right, let's look at this question. So in a circuit for finding the resistance of a galvanometer by half deflection method, okay, a 6-volt battery and a high resistance of 11 kilo ohm are used. Okay, now there is hint in the question, a high resistance. So when we are using this half deflection method, we are using a high resistance. We see this 11,000 ohm, 11 kilo ohm over here. Okay, that is a key information that has been supplied in the question. The figure of merit of the galvanometer is 60 microampere per division. Okay, figure of merit of the galvanometer. So basically all it means is for how much current it is going to move by 1 division. That's all. So you know how the galvanometer works. Current flows and then proportionately they have the deflection in the galvanometer. So for 1 division, it means that a current of 60 microampere has flown. That's all it means. It has just been given a very fancy name. That's all it means. Now in the absence of shunt resistance, which is we are talking about this circuit, the galvanometer produces deflection of theta is equal to 9 divisions. And when current flows in the circuit, okay, the value of the shunt resistance that can cause the deflection of theta by 2 is closest to. Okay, so what is the question over here? Now we are talking about a scenario where the galvanometer is connected like this, and there is no external shunt. There is no shunt that has been used. Now in this case, the divisions, there are 9 divisions, the deflection of 9 divisions in the galvanometer. Okay. Now when we have added this shunt to the galvanometer in parallel, then we see that the deflection is half. That is, it is going to be 9 by 2. The deflection is going to be 9 by 2 in the galvanometer. So we have to find out what should be the value of this shunt resistance. That is the question. Is that correct? Okay. Are you comfortable with the question? Now before we proceed with this question, do you have any ideas? How do we go about approaching this problem? It's not necessary that quickly you should be able to solve this problem. We're going to solve it anyway, but I want to know what approach are you going to take? So Gopal is saying, I think B is the answer. I don't really know which option is the correct answer, Gopal, but I would love to see your approach. What is the approach you have used to solve this question? That is the most important thing. If the approach is right, the answer most likely would be right. What is the approach that we should take in this question? Any ideas, guys? So don't be worried about the names that have been given. Okay, don't be worried about the names that have been given, as in this is half deflection method. It's all circuit. Okay, it's all circuit. That's all. So Tanmay is saying unit deflection into theta. You're absolutely right. That is going to give us the current. You're absolutely right. What does a shunt mean? So shunt is simply a resistance which solves a purpose. Okay, it is used to alter the resistance of the galvanometer in a useful manner. Okay, if we have to convert it into a voltmeter, we use the shunt in some manner. If we have to convert it into a ammeter with a higher range, we use it in another manner. So it's just a resistance, simply a resistance which is used in a particular fashion and connected to the galvanometer. All right. Now let's see. Okay, so can we find what is the current over here? Now the current is already given. When there is no shunt attached, the current is already given. How do we know the current is given? We know that it is 60 microampere per division. And the deflection is by how many divisions? The deflection is 9. So what will be the current? The current is going to be 9 into 60 microampere. Simple. Is that correct? So we know what is the current flowing in this case. Okay. So can I say that the current is going to be equal to the voltage and the resistance of the galvanometer and this 11,000 ohm resistance, they are in series combination. Can we see that? Of course they are in series combination. So what will be the net resistance? It is going to be Rg plus 11,000. Correct? And what is this current? What is this current? This current is going to be 9 divisions multiplied by 60 microampere. So I'm converting that to ampere, of course. Alright, so this is 9 into 9 divisions into the value of 1 division is 60 microampere. So 60 into 10 to the power minus 6 ampere. Is that right? Now this tells me very easily that I can find what is the value of Rg. Okay, this tells me that Rg is going to be equal to, so this 6 and this 10 we will have here, this 10 is going to make it 10 to the power minus 5. So we can say that Rg plus 11,000 is going to be equal to 10 to the power 5 divided by 9. Is that correct? So what is 10 to the power 5? I can write it as 1 followed by 5 zeros, yeah, and then divided by 9. So Rg will come out to be, so 10,000 divided by 9, if you can calculate that very easily, if you divide by 9, it's very simple. So 9 ones are 9, and then you have 1 as remainder, then you'll have 10, then again you'll have 1, and again you'll have 1, again you'll have 1, and so on. Okay, divided by 9 is very simple. Minus 11,000. So the value of the resistance of the galvanometer comes out to be how much? It comes out to be 111.11 ohm. I'm going to approximate that as 111 ohm. Tanmay is saying, I think the question is actually easy, but the language is tricky. Spot on, Tanmay. Spot on. And that's why I always say, don't get bogged down by the language. Okay, the longer the question is, chances are the shorter would be the solution. Okay, and we are going to see how easy is the solution. Okay, perfect. So we have calculated what is the resistance, and that is 111 ohm. Now comes the conceptual part. This is the most important part over here. All right, now the current here is I when there is a galvanometer over here. Okay, now this current, now look at this current. This current is 6 divided by Rg plus 11,000. Now Rg, so this 11,000 has a very high value. It is given in the question that it is a high resistance, which means that this resistance is much higher with respect to Rg. Okay, which means that the current is majorly because of this 11,000. Now if I change the value of Rg, the current is not going to vary much. Do you agree? Okay, this Rg is going to be very small with respect to 11,000. So in order to find the current, we can neglect Rg also. Okay, So if we change the value of Rg, it is not going to make much of a difference to the current. And that is the key part of this question. Now when we are attaching this shunt, the resistance of this S and Rg, so they are in parallel combination, so the resistance is going to change. But even the changed resistance, in this case, what will we write the current as? In this case, we'll write the current as 6 divided by 11,000, and whatever is the, let's say, R prime, whatever is the equivalent resistance of S and Rg. Okay, so R prime. Now again, this R prime is going to be very small compared to 11,000. Okay, so if you're connecting S and Rg in parallel combination, then the equivalent resistance is going to be smaller than Rg, right? So this is going to be even smaller than Rg, which means it makes no difference to the current. So now we can say that since this resistance is not going to make much of a difference, the current here is still going to be I. Okay, the current here was I, the current here is still going to be I. Is that correct? Okay, and now what we have seen is that now in the galvanometer, the deflection is half. Okay, that's why it's called the half deflection method. The deflection is half, which means that the current going here is also going to be half. So if I by 2 is going here, I by 2 is going to go over here. Is that correct? Okay, so now we have seen that this current is going to be equally divided between S and Rg. And when is the current equally divided? When both the resistors are same. Okay, when is the current equally divided into two parallel branches? When the resistors of both those parallel branches is equal. Okay, so if they're equal, the current is going to get divided equally, which means that simply S is going to be equal to Rg. That's it. S is going to be equal to Rg, and that is approximately going to be equal to 111 ohm. And that is going to be my answer. Is that right? Okay, so I would say very conceptual question. If you start solving it using a circuit, if you don't make use of this being a high resistance, then this calculation is going to be extremely tedious. Okay, you'll find it very difficult to do the calculation, but it is given in the question that this is high resistance, and so we have to make use of that. And once we make use of that, once we are clear with the concept, then solving this question is not difficult at all. Okay, so I hope this is clear to you. If there any confusion, do let me know, and if not, do let me know what is the difficulty level for this problem. Okay, so approximately, so the option is closest. The closest option we have is 110 ohm, so that is going to be the right option. Okay, 111.11 ohm is my answer. Great. That's awesome that you have figured that out, and I hope you have used the correct concepts. Okay, some people are finding it difficult, some people are finding it easy. That's all right. I won't say it was very straightforward, but it all boils down to concept. Okay, we need to make use of the information that is provided in the question. All right, so if that is clear, let's move to the next problem. Okay, so we are talking about electrical instruments. And another very important electrical instrument is the potentiometer. Okay, so let's solve a question on potentiometer. Okay, again the question is lengthy. But let's take that up slowly. Don't be worried about the solution. Just go through the question and see if you can understand the question first. Okay, so we have a potentiometer PQ set up. So you have this potentiometer over here. You know what is the setup for a potentiometer. And we have to compare two resistances as shown. What resistances? R1 and R2. The balance point is at length L1 centimeter from P when two-way key K3 is plugged between 2 and 1. Okay, so what they're basically saying is that when this key is closed, okay, when this key is closed, then the balance point is found at L1 distance from the point P. Okay, and then they are saying that when this key is closed, the key between 1 and 3 is closed, then the balance point is found at L2. And using this data, we have to find out what is the ratio of the resistance R1 and R2. Is that correct? All right. Is the question clear? I know it's a long question, so I'm going to keep it here for some time, go through the question and let me know if the question is clear. It's a slightly long question, but what it means is pretty straightforward. Okay, what it means is pretty straightforward. Okay, what does it mean? So one thing it is given to us is that this ammeter reads 1 ampere. Okay, in the external circuit, this ammeter reads 1 ampere. Now when 1 and 2 is connected, then the null point is found at L1 distance, and when the key between 1 and 3 is connected, then the balance is found at L2 distance. Okay, the null point is found at that distance. Is the question clear? Alright, so my question to you is, how do we use a potentiometer? How do we use a potentiometer? How do we go about approaching this problem? Okay, first I want to know from you, and then we are going to proceed with the solution. The total length is not given. True, Tanmay, the total length is not given. Anmol, I don't know which option is correct. So when we solve it, we are going to know the correct option. But what I want to know from you is, how do you approach this problem? Any ideas? Alright, Captain Jack Sparrow is saying by taking potential gradient. Excellent answer by taking potential gradient. Yes. And what else? By applying KVL, not so sure about that. We probably don't need to apply KVL. P by Q, if you mean the ratio of resistance is L1 by L2, not really. It's not going to be L1 by L2. Okay, we need to look at the circuit more carefully. Alright, let's understand how the potentiometer works. So this is the potentiometer wire PQ. Now when we calibrate this potentiometer, what we basically do is that we find what is the potential drop from P to Q. Okay, when we are going from P to Q, we find out what is the potential drop V, and we also know what is the length of the wire. So we define something called the potential gradient. Okay, what is potential gradient? Per unit length, what is the potential drop? That is called the potential gradient. So the potential gradient is going to be V by L, and that I am calling it K. Okay, so which means that per unit length of the wire, okay, what will be the potential difference? What will be the potential drop? Is that correct? Okay, so the potential gradient I'm going to say is going to be K. V is the total potential drop across PQ, and L is the total length of the potentiometer wire. Okay, so basically it means that if we go from P to Q, the length we have traversed is L, and hence the potential drop is V. So per unit length, what will be the potential drop? That is V by L, and that is going to be a constant for a potentiometer, and when we calibrate the potentiometer, we find that potential gradient. So I'm calling that K. It might be some number K. Okay, clear? Okay. Now what we have done is we have closed this switch, and the current here is 1 ampere. Okay, the current here is 1 ampere. Now we have closed this switch. Now when we have closed this switch, now see what the circuit is. Now this part of the circuit is an open circuit. Is that correct? So from this point to this point, you don't need to look at this circuit. Just forget about that circuit. It is an open circuit, so it is not part of our circuit. Just forget about that. Okay, we have forgotten about that. Okay, now the important thing is that this key is closed, and hence this galvanometer over here has been attached to this point, and here we are finding the null point. What does the null point mean? It means that there is no current through the galvanometer. That's what null point means. There is no current through the galvanometer. And when are we going to have no current through the galvanometer? When the potential difference between these 2 points is the same as the potential difference between these 2 points. Is that correct? Let me show that to you again. So what we are basically saying is that there's going to be no current through the potentiometer, through the galvanometer. So there is no current in this branch. Okay, can you see that? There's going to be no current in this branch. And when is that possible? When is it that there is no current between two branches? When both of them are at the same potential difference. So these 2 points and these 2 points are going to be at the same, between the same potential difference. Do you agree? Is that absolutely clear? Okay. And what do we have here? This null point has been found at L1. Correct? So there is no current over here, and when this 1 ampere current is coming over here, is there going to be any current in this branch? No, there's going to be no current in this branch. Okay, because they are at the same potential. So there's going to be no current flowing here. So this entire 1 ampere is going to flow through this branch. Do you agree? This entire 1 ampere is going to flow through this R1. Is that correct? Are we clear up till this point? Okay, if up till this point, if it is clear, then solving this question is just, it'll take just 1 minute. Okay, but we are going over the important aspects. We're going over the important concepts. Now do let me know if this concept is absolutely clear. Otherwise, I'm going to explain it again. This is the crux of the problem. How a potentiometer works. If it is not clear, if you have a slight difficulty, do let me know. I'm going to go over it again. Don't worry about that. Sure, Captain. I'm going to explain that to you again. I'm going to explain all of this again. We are in no rush. Okay, let's see. So we have this potentiometer wire. Okay, sure, I'll go over it again. Not a problem at all. Okay, so don't look at anything above it. Okay, so the arc I have drawn, don't look over it. Don't look above it. Okay, just look at the circuit which is below it. Okay. Now let's say between this point P and Q, the potential drop is V. Okay, obviously it is a resistance. Okay, so there's going to be potential. So there's going to be some current over here. So there's going to be potential drop across PQ. Let's say that potential drop is V. And let's say that the length of the potentiometer wire is L. So per unit length, what is going to be the potential drop? Per unit length, the potential drop is going to be V by L. So when we go from here to here, when we are traversing a length of L, the potential drop is V. So if we are going over unit length, what will be the potential drop? It is going to be V by L. This is called the potential gradient of a galvanometer, and it is going to be a constant for a particular potentiometer. Is that correct? Any problem here? Is that clear? Alright, now let's look at the circuit above. Now what we have done is we have connected point 2 and 1. Okay, we have closed the key between point 2 and 1. So this is connected. Okay, this branch is connected. Now this branch over here is open. This key is not closed. Okay, so we don't need to worry about this branch. Just let it be. Okay. Now we have found the null point over here, haven't we? We have found the null point over here. What does it mean to find the null point? When we find the null point, it simply means that there is no current through the galvanometer. Okay, we find that point where there is no current through the galvanometer. So the current in this branch is going to be 0. Okay, there is no current through the galvanometer, which means the current in this branch is going to be 0. Do you agree? Alright, is this clear so far? Now what does it mean? Now if there is no current flowing from this point to this point, what does it basically mean? It means that there is no potential difference. Okay, so if there is no current flowing through this branch, what does it mean? It means that this point over here and this point over here are going to be at the same potential. Okay, now this point and this point are already at the same potential. They are simply connected by a wire. Okay, so what does it mean? It means that whatever is the potential difference across R1 is the potential difference across this length of the wire. Okay, what length of the wire? This L1 length of the wire. So I'm going to show that to you again. I'm going to say that again. Whatever is the potential difference across this resistance R1 is the same potential difference across these 2 points. And what are these 2 points? These 2 points have a resistance which have a length L1. Is that clear? Okay, so the potential difference across these 2 points is the same as the potential difference across these 2 points. Is that correct? Okay, perfect. Now what we have seen is there is no current in this branch and there is no current in this branch. Okay, because the potential difference across both the points is same, so there is no current. What does it mean? It means that this 1 ampere that is coming from here, is it going to get divided into this branch? No, all of that 1 ampere is going to flow in this manner. Is that clear? Okay, now is this clear? So all this current 1 ampere is going to flow through this branch. Okay, now what does it mean? It means what is the potential difference across R1? Okay, the potential difference across R1 is going to be IR. Simple. So what is the potential difference across R1? The potential difference across R1 is the current 1 into the resistance R1. Okay, so that is the potential difference. Now, what is the potential difference across this length of the wire? Which length of the wire? L1 length of the wire. What is the potential difference across this length of the wire? And here we are going to use the potential gradient. So per unit length, what is the potential drop? K. Per unit length, what is the potential drop? K. So for this length L1, what will be the potential drop? It is going to be K into L1. That's it. Right? So per unit length, the potential drop is K. So for L1 length, what will be the potential drop? The potential drop is going to be K into L1. Is that correct? That is the first equation we have got. So 1 into R1 will be equal to KL1. Is that correct? Absolutely, Tanmay. You're absolutely right. Pinky is saying this, so the screen is blurred. Please try refreshing it. Probably that will help. Okay. Now this is done. This part is done. Okay. So we are going to write it over here. So 1 into R1 is equal to K into L1. That is what we have figured out from the last evaluation. Now what we are doing? Now we are joining these 2 points. Okay, now the key between 1 and 3 is closed. What does it mean? It means that this circuit is now open and you can take it and throw it out of the circuit. Okay, you can throw it out of the diagram. Don't concentrate on that part of the circuit. Perfect. Now the null point has been achieved at L2. Okay, now the same thing is going to happen. The current is going to be 1 ampere through this branch, and listen to me very carefully. There is no current through this branch. Now look at this. What does it mean? Now what are the points? This point and this point. The potential difference between these 2 points, let me name it. X and let me name it Y. So the potential difference between points X and Y is the same as the potential difference between points P and Z. Can you see that? This point, same potential. This point, same potential. Because there is no current going through the galvanometer. Is that right? Okay. Now do we need to do all that again? No. What is the potential drop? This is 1 ampere and this resistance R1 and this resistance R2 are in series. So what is the total potential drop? The potential drop is 1 into R1 plus R2. And this potential drop is equal to K multiplied by, for unit length the potential drop is K, for length L2 the potential drop is going to be K into L2, and that is going to be my second equation. Is that correct? Now all I have to do is I have to divide these 2 equations. So let's divide. So R upon R1 plus R2 will be equal to L1 by L2, just to get rid of K, because that is not required. Okay, that is the variable we had assumed, so that is not required. So R1 upon R1 plus R2 is going to be equal to L1 upon L2. Now you can evaluate this very quickly. So R1 L2 is going to be R1 L1 plus R2 L1. Okay, so what do we need? We need R1 upon R2. So we need R1 upon R2. So that is going to be L1 divided by L2 minus L1. Okay, and that is going to be my answer. Is that clear? Okay, so the potentiometer question, they can be asked in various forms. Okay, there are so many different kinds of ways in which potentiometer questions can be asked. But the concept is very simple. Okay, if you have found the null point, then whatever is the potential difference between these 2 points will be the potential difference between these 2 points. That is the basic crux of the potentiometer, how a potentiometer works. Alright, so I hope that is clear. So we have time for just one more question. So let's quickly do that. And there's another, so this is another very interesting question. So this is a question based on meter bridge. Okay, this is a question based on meter bridge, but this is not a straightforward question. Okay, it has a slight twist, a very interesting twist. Okay, so in a meter bridge, the wire of length 1 meter has non-uniform cross section such that the variation dr by dl of its resistance R with length L is given by dr by dl is proportional to 1 upon root L. Okay, now generally the wire has uniform resistance, but in this case the wire has non-uniform resistance, and dr by dl, okay, the change in length per unit, the change in resistance per unit length is proportional to 1 upon root L. Okay, so this is not uniform resistance. The resistance is varying in this fashion. Now two equal resistances have been connected. So we have this R prime and this R prime, which is connected in these two slots, and the galvanometer has zero deflection when the jockey is at point P. Okay, when the jockey is at point P, there is no current through the galvanometer. Okay, so basically what is a meter bridge? A meter bridge is simply a balanced Wheatstone bridge. So here you have one resistance, here you have the second resistance, here you have the third resistance just to the left of the null point, and here you have the fourth resistance, and this galvanometer is between the bridge. The galvanometer is between the bridge. So you can see very clearly this is a Wheatstone bridge. It's a balanced Wheatstone bridge. And when we have a balanced Wheatstone bridge, then what can we say? That the resistance R1 by R2 should be equal to the resistance R3 by R4. Okay, that is a balanced Wheatstone bridge. Okay, now these two resistances are equal, which means R3 by R4 should be equal to 1. Is that correct? Okay. Tanmay is asking non-uniform potential gradient. We're going to come to that, Tanmay, in just a moment. When we are solving this, we're going to come to that. Okay. No, but the crux of the problem is that these resistance R1 by R2, they are equal resistances. So this should be equal to R3 by R4. And what is R3? R3 is this resistance, and R4 is this resistance. Is that clear? Okay. Is the basic clear? Perfect. Okay, now it all boils down to finding what is the resistance. So we have to find out what is this resistance R3 and what is this resistance R4. So R3 is the part of the wire from A to P, and R4 is the part of the wire from P to B. Okay, now here we are said that dr by dl, this is proportional to 1 upon root L. Okay, so as L is changing, the change in resistance per unit length is proportional to 1 by root L. Okay, what does it mean? It means that if we are here, let me draw it over here. Okay, let's see, we are over here. Okay, so let's say this length is L. From this end, this length is L. From this end, the length is L. Now for this length, if we slightly, when we are at this length already and we slightly go ahead by dl, so there will be some change in the resistance also. So this will have some resistance R, this will have some resistance R plus dr. Is that correct? So for this change in length dl, the resistance has increased from R to R plus dr. Is that correct? So the change in the resistance, which is dr, divided by the change in length, which is dl, is proportional to 1 upon root L. Okay, it's going to be proportional to 1 upon root of this length over here. This is the meaning of dr by dl proportional to 1 upon root L. Is that correct? Okay, perfect. So now let's go ahead and solve it. So what we see here is that the resistance is a function of L. So we need to find out the resistance as a function of L. Okay, we need to find out what is the relationship between R and L, and for that we are going to use this expression. Okay, so now there is a proportionality sign, so we are going to get rid of the proportionality sign and we are going to put a proportionality constant, and this 1 upon root L, I'm going to write it as L to the power minus half. Okay, I hope that is clear. So dr upon dl, not dt, I'm sorry, dr upon dl is equal to k into L to the power minus half. Okay, so that tells me that dr is going to be equal to k into L to the power minus half into dl. And now what we need to do? It's obvious, we need to integrate on both sides. So when L is equal to 0, which means which point? Which means this point A. When L is equal to 0, obviously there is no part of the wire, so the resistance is going to be 0. And when this L becomes equal to L, so basically when the length becomes equal to L, it could be anything, then we are saying that the resistance is going to be R. Okay, so when we have reached a point L, we have reached a length L, then whatever is the resistance between the 2 points, the starting point and this point, that is going to be the resistance R. Is that correct? Perfect. So integrating dr, we are going to get R, and this is going to be equal to K into, we are going to integrate L to the power minus half. So this is going to be minus half plus 1. So L to the power half, but we also have to divide it by half, so that is going to make it 2. So we are going to get R is equal to 2K into root L. Okay, so for a length L, the resistance between the starting point and length L is going to be 2K into root L. Is that clear? Do you have any confusion with this derivation? Okay, so effectively, Tanmay is asking how to take limit for R. Very simple, Tanmay. See, this is our wire. This is our wire. So when we are at L equal to 0, we are here. So if we are at L equal to 0, we are taking no length of the wire. So what will be the resistance? The resistance is going to be 0. And let's say when we have reached point L over here, we have reached an length L over here. So whatever is the resistance of this part of the wire, we are calling that R. Okay, whatever is the resistance of this part of the wire from the starting to length L, that has a resistance R. That resistance we are calling is R over here. That's how we have taken the limit. Okay. So now what do we have? We have this R is equal to 2K into root L. So we have R is equal to 2K into root L. Now listen to me very carefully. Okay. Now we are talking about this part of the wire. What is the length of this part of the wire? This is resistance R3. Okay, this is resistance R3. What is the length between this part of the wire? The length is L, and this length is from the starting. Okay, from where are we taking the length? We are taking the length from point A. Okay, so what will be the resistance R3? The resistance R3 is going to be 2K into, for this length we are going to substitute L, so this is going to become root L. Do you agree? Perfect. Do you agree with that? So this resistance here is going to be 2K into root L. Now what do we need to find out? We need to find out this resistance R4. But this resistance R4 obviously is going to have a length of 1 minus L. Okay, 1 is the total length. So this resistance is going to have a length of 1 minus L. But is this length being calculated from A? Is this length 1 minus L being calculated from A? No, we are taking it from here. But in my derivation, I have taken the length from here. So we cannot directly calculate that. Okay. So what we'll have to do is, we'll have to calculate the resistance of the entire wire. So this is R3, this is R4. Now if we talk about the entire wire, the length is 1 meter, and this 1 meter we are taking from the starting point. Okay. So now the length of the entire wire, for that the resistance is going to be R3 plus R4. Do you agree? The length for the entire wire, the resistance is going to be R3 plus R4. This is R3 and this is R4. So R3 plus R4 is going to be 2K, and what is the length? The length is 1 meter, so this is going to be root 1. Is that clear? So from here, can we find out what is R4? R4 is going to be 2K root 1 minus R3. And what is the value of R3? R3 is 2K into root L. That is how we are going to find R4. So this is the value of R3. This is the value of R4. And we have seen that R3 by R4 should be equal to 1 because these resistances are equal. Okay. So what do we get? R3 is 2K upon root L divided by R4 is 2K root 1 minus 2K root L, and this is equal to 1. Correct? So what do we get? 2K, 2K, 2K gets cancelled. So root L is equal to 1 minus root L. Hence 2 root L is equal to 1. Hence root L is equal to 1 by 2. And hence L will be equal to 1 by 4. Okay, so the length is going to be 1 upon 4 meter. This value of L is going to be 1 by 4 meter, where we find the null point. Okay, so my answer should be L is equal to 0.25 meter. Is that clear? Okay, very interesting question. It was not a straightforward question at all. It was a very a good twist to the good old meter bridge question. Okay, but I hope you were able to follow. Alright guys, so that is it for this session, and do tune in every week, because we have sessions every week and we're going to solve interesting problems. We're going to solve all the interesting concepts so that it gives you a push for your revision. Okay, so I hope this session is helpful for you. Keep attending sessions. Good to see all the familiar faces. Keep coming back, and till we meet again, take care and have fun.